String theory was supposed to be a theory of everything. Deep down, so the idea everything is made of tiny wiggling strings. The most interesting thing about string theory so far has been that it never attracted as much attention as it did because, despite the grand claims, it turned out to be rather useless. Until now. Because I just came across a new paper with the most lovely use of string theory. Let's have a look. As a theory of everything, string theory needs to be made into a quantum theory. It's this quantum version that then requires 10-dimension supersymmetry and a multiverse. This caused a lot of problems without ever actually solving any. In the past 10 years or so, the interest in string theory as a theory of everything has collapsed, and I think it's for the better. That said, string theory as a mathematical framework is so general, you'd expect it to be useful for something else. Physicists have tried, for example, to use it to describe the quark-gluon plasma of certain types of metals, but it didn't work well, and not much came out of it. This new research now comes from an entirely different direction. It comes from a group who works on network theory. I don't mean social networks in particular, but general networks that are everything made of some sort of nodes connected by links. The cool thing about networks is that they describe a huge variety of things, anything from economics to chemical reactions to materials to blood vessels. The new paper looks in particular at the latter, biological networks like blood vessels and neurons. The previous theory had it that these grow under the constraint that the network keeps the total length of the branches to the minimum necessary for function. If you assume that the network grows with this constraint, keep length minimal, you get a very specific kind of geometry. In particular, you get branches that split in two, not three or more. And these two outgoing splits lie in the same plane as the ingoing one. It's called a Steiner tree. The Steiner tree is beautiful maths, but unfortunately nature didn't read the textbook. If you look at real biological networks, plants, roots, neurons, blood vessels, and so on, that's not what they look like. This problem has been open for a long time. The authors now said, okay, maybe the issue here is the quantity we're optimizing for. Let's not look at the network in terms of the volume, but in terms of its surface area. You basically have a lot of connected empty channels now, and that looks very much like the interactions they use in string theory, in particular with what's called closed strings. Closed strings are basically loops. If you depict their motion in time, then they sweep out an empty tube. If they split into two, then that looks kind of like upside-down trousers. And that is very similar to the problem that these network people were looking at. And so they literally took the string theory maths, the number Goto action in particular, but without quantum effects, and used that to minimize the surface area of the biological networks. String theorists have spent decades developing mathematical tools to find surfaces with minimal area, especially when those surfaces branch and merge. And the equations are the same. That turned out to work very well. They get three-way splits and they don't lie in a plane either. Better still, there's good explanations for it. It's that the symmetry is broken because the outgoing channels don't have the same width, so they don't have the same surface area. If they take a limit where the channels are all very thin compared to the typical distance between nodes, they recover the Steiner tree with only two splits and planar symmetry. But the string theory approach successfully generalizes this. The authors also check their results against data, human neurons, fruit fly neurons, blood vessels, trees, corals, plants. The statistics line up remarkably well. The frequency of the three-way junctions, angle distributions, the prevalence of right-angle branches all match the predictions of the string theory model. Interestingly, the model doesn't just work for networks whose branches are genuinely hollow like blood vessels, but any for which the growth requirement is minimized surface area for one reason or another. That might be to minimize material or tension or interactions with the environment, etc. So the model is much more general than it sounds at first. I give this a 0 out of 10 on the bullshit meter. I find this a remarkable paper for various reasons. One is that it's an idea of the why didn't I think of this sort? Like, it seems so obvious, doesn't it? The second one is that it's a lovely example of how interdisciplinary research can be useful. The third and maybe most important reason is that it's got genuinely practical implications, not just to understand how these biological networks grow, but also for design purposes in, say, microfluidic devices or to understand how certain materials behave. So after 40 years, string theory finally found its destiny and its fruit fly neurons. I wonder what Ed Witten would say about this. Hello? Hi, Ed. Well, at least it's a theory of something. Fruit flies in 10 dimensions. Go for it, I say. Bye. Dark matter supposedly makes up 85% of the matter in the universe. Astrophysicists say it's some mysterious stuff, very unlike the matter that we see around us, probably some sort of new particle or a new force or a parallel universe. I wish this was a joke, but it isn't. A new paper now argues that dark matter might just be normal matter. And to add insult to injury, the idea isn't even new. It's been around for 40 years. It's just that no one paid much attention. Well, that's quite something. Let's have a look. Astrophysicists have a lot of observations that tell us that dark matter can't just be normal matter, or so we thought. The most important clue is that, well, it's dark. More precisely, it doesn't interact with electromagnetic radiation at all, neither with light in the visible part of the spectrum nor with radio waves. This immediately rules out most of the particles around us, because everything that has an electric charge interacts with electromagnetic radiation. The only particles that are left then in the standard model are the Higgs and the Z boson, but those are highly unstable, and the neutrinos are not heavy enough to properly form structures. Physicists have gone through these arguments and circles for decades and always concluded it needs to be a new particle. Preferably one with a catchy name that sounds good in grand proposals. But now they're having a second look at an idea that goes back to no other than Ed Witten in 1984. He suggested that quarks, the particles that make up protons and neutrons, could form bigger clumps. These clumps could be stable and they'd be electrically neutral, so they wouldn't interact with light. They'd be dark. They'd fit the bill. These objects are sometimes called quark nuggets. Normal matter is made from up and down quarks. These are the two quarks with the lowest masses. But Witten figured out that if you have a lot of up and down quarks, this is not energetically the best state. You get a state that's energetically more favorable if you add some of the next heavier quarks, the strange quarks. And because this combination is energetically more favorable if the quark clump is large enough, it doesn't decay, it's stable. This is a particular type of quark nuggets called strangelets. The size of the strangelets is important for that to work. Small combinations of quarks with strange quarks are unstable. We know this because we can create those in particle colliders. But if Witten's maths is correct, and who really wants to question Witten's maths, then large chunks should be stable. We can't produce these large strangelets in particle colliders. There just aren't sufficiently many quarks in the collisions, but they could have been produced in the early universe. And because they're stable, they just remain there, sitting around, being dark and heavy. Indeed, even tiny strangelets are enormously heavy. If you had a strangelet the size of a tiny dust grain with a radius of about 10 micrometers, that'd weigh about a ton. Yes, you heard that right. If it had a radius of a centimeter, that'd be about 1 billion tons. You have to admit that quark nugget is an adorable name for something that might weigh a mountain. The idea first caused some excitement and then it caused some panic because the quark matter with the strange quarks is energetically more favorable than the stuff that we are made of. Physicists worry that if you could make just one stable strangelet in a particle collider, it might start converting all our ordinary nuclear matter into strange matter and eat the entire entire Earth. It'd be a similar problem to chemical polymorphs that the science fiction story Ice 9 is about. Those fears turned out to be unfounded because we can't produce the stuff in colliders. Even if some of the strange matter came by from outer space, it can't convert the normal matter because that only works at super high densities. The idea that strangelets make up dark matter fell by the wayside because it relied on a specific assumption about the early universe that turned out to be wrong. You see, in the early universe, we have this soup of quarks and gluons called a quark-gluon plasma. The plasma cools, and at some point it starts to clump into smaller pieces like neutrons and protons. This is a phase transition, much like when water vapor condenses to droplets. Indeed, in the 1980s, physicists thought that the phase transition in the quark-gluon plasma is similar to that of water. It's what's called a first-order phase transition. And in such a transition, you can get big drops of those strangelets, which then just continue to sit around as dark matter. It then became clear, though, that the phase transition in the quark-gluon plasma just isn't first-order. It's instead a rather well-behaved crossover, and that doesn't make bubbles to create the strangelets. Now, however, physicists are rethinking this for two reasons. The first is that they found that while a first-order phase transition would do the job, it isn't necessary. Even without bubbles, there can be strong correlations in the plasma that can allow large clusters to form. The second reason is that physicists have found that quark matter can do peculiar sort of superconductivity that conducts not electric charge, but color charge. It's called color superconductivity, and it enhances the stability of quark matter. Take this together, and it turns out that strangelets can form in the early universe after all. Theoretically, they could weigh anything from nanograms to asteroid scale. There are other types of quark nuggets that physicists are reconsidering now besides the strangelets. The next most popular one is one that's stabilized by axions. These axions are hypothetical particles that many physicists believe exist. It's somewhat difficult to make up dark matter just of axions. However, combine the axions with quark matter and it works nicely. Quark nuggets have some specific experimental signatures. The most obvious ones are that if they hit our planet or maybe the moon, they'd leave traces like little tunnels. If they hit stars or white dwarfs, they could also convert the nuclear matter, leaving behind stars that are oddly compact or white dwarfs with weird spectra. But basically, the signatures are subtle and difficult to find, which fits all too well with our observations, doesn't it? Well, if this idea is right, then the biggest problem in cosmology wasn't missing matter, it was missing attention. Physicists have shown that the past can be changed in quantum physics. That's either very impressive or nonsense. You can't really change the past, can you? And yet a new paper by two physicists claims exactly this, at least in quantum physics. Let's have a look. Quantum physics works extremely well. It predicts experiments with absurd accuracy, but conceptually it's a disaster. In quantum physics, we describe everything by something called a wave function, usually denoted with the Greek letter psi. From the wave function, we can calculate probabilities for measurement results. But what is the wave function? Is it anything? Is it real? And what happens if you measure it? Physicists have debated this for more than 100 years, which in physics counts as still early days. One of the most important arguments in this debate goes back to Eugen Wigner. He was trying to make sense of what happens in a measurement in quantum physics. Whatever a measurement is in detail, it has the effect of converting the possibilities that the wave function describes into tangible outcomes. Before you make a measurement, a particle can do strange things, like being in two places at once. After you measure it, it must have decided on one. Wigner said, okay, but suppose that someone produces a particle so that it's in two places at once, let's say left and right at the same time, and then he measures the particle and finds it left. We know how to describe that. But now suppose that this person has a friend who waits outside the laboratory and who hasn't seen the measurement outcome. For this friend, the entire laboratory is in a state where the outcome of the measurement was left and the outcome of the measurement measurement was right until the person opens the door and looks at the result. Sounds absurd? It is, but this is what quantum physics seems to say. Now, normal people might have left it at this, but physicists are anything but normal, and so they've instead derived theorems about the absurdity that ensues. A particularly famous one is fairly recent and goes back to Frauchinger and Renner. They said that if you duplicate this setup with the experiment and their friend, so that you have 2 experimenters and 2 friends, and you make sure that the particles that the experimenters are working on are entangled, then there are cases where there's no combination of measurement results that all of them agree on. This seems to demonstrate that measurement outcomes either are not objectively real or that all measurement outcomes are objectively real, but each in its own universe. The new paper now is a new twist on this idea in which the 2 experiments with their friends are not done at the same time, but after each other. An observer measures a quantum system and gets a result. Later, another observer can either check that result or discard the measurement and do a new one. If the second observer checks the result, then, well, they find the same thing. If they discard the measurement and do a new one, the result of the second measurement depends on what the first was, and the stunning thing is that there are possible outcomes for the second measurement that are incompatible with any definite result of the first measurement. It's like the first measurement wasn't real. They have erased the past. Okay, you might say, but just exactly what does it mean to discard the first measurement? They mean that, in principle, the interactions that made the measurement happen, say a particle that hit an atom and emitted a few photons, can be undone. This should be possible because in quantum physics, any process can be reversed in time. Indeed, there are some experiments in which this has been done. They sometimes make headlines saying that physicists have turned back time or something, but really it's just performing operations so that you undo exactly what happened previously. So this is what they rely on, that you can reverse this measurement. And the conclusion is then that in quantum physics, you can't treat past events as something that definitely happened or didn't happen. Even the history of a particle might both have happened and not. It's either that or each history happened in a different universe. What are we to make of this? I think this argument is formally correct and it's a real mind-bender, but the conclusion that I draw from this is an entirely different one. It's not that the past has no definite events, rather it's that if you can reverse a measurement, then it wasn't a measurement. That is, to me, the paper shows that we still don't understand what a measurement really is. So I give this a 2 out of 10 on the bullshit meter. Nice paper, but with flaws in the interpretation. That said, I agree on the overarching point that quantum physics is difficult to reconcile with our everyday notion of causality. There is something very weird going on at the intersection of quantum physics and time that we haven't yet figured out. And this paper might be a step on the way, or at least a very scenic detour. Thanks for watching. See you tomorrow.